Okay, so let's start from O levels. Let's build up on O levels. So basically, in atomic structure, the atomic structure in O levels, atomic structure. This will be our first chapter for AS. Then we'll move on to chemical bonding, and then we'll try to do moles after that. Okay, but first atomic structure, then chemical bonding. Chemical bonding is a quite long chapter, so we'll try to cover it, and then we'll move on to moles. And moles is pretty easy. It's not hard. You just have to get used to it again. So O levels recall, or I should say IGCSE recall. And O levels used to say that what are atoms? Atoms are the simplest particle of matter, right? If you break down matter, if anything is matter which occupies space and has a certain mass, we call that matter. Okay, so basically if you break down matter into smaller and smaller pieces, the last smallest piece that you'll be left with is basically an atom. You cannot break an atom further into anything that is identifiable. Okay, so the last identity of the matter is an atom. So if you break down matter into simple pieces and pieces, the last thing you'll be left with is an atom. And you can't see atoms with your bare eyes. Even microscopes, you can't see atoms with microscopes. You need a special kind of microscope to like visualize atoms. So secondly, atomic structure from O levels, we used to say that an atom would have two regions. There's this nuclear region in the middle, which we call the nucleus, in which there is a nucleus. This is the nuclear region. And out of this nuclear region, you have the extra nuclear part of the body of an atom, right? And that extra nuclear part basically consists of shells or energy levels, if you might recall. Okay, so we have extra nuclear part and we have a nuclear part. The nuclear part consists of a nucleus, and the extra nuclear part, apart from the nucleus, would contain the shells. Okay, so these are the two main regions in an atom or in the structure of an atom. Now you also have the body parts of an atom. The body parts of an atom are basically the subatomic particles. Subatomic particles. There are three types of subatomic particles that you should know, and you should know how to find them by looking at an element's symbol and the numbers written with it. So basically, you have three types of subatomic particles. The first one is positively charged subatomic particle. It's known as a proton, and the symbol is P with a small positive on the exponent, right? Then there's electron, which has a negative charge. So it is a negatively charged subatomic particle. And you have a neutron which has zero charge. Basically, it is neutral. So you have a neutron. There are three subatomic particles. These are the body parts of an atom that are going to be included in the atomic structure, right? So there are two types of subatomic particles that are present inside the nuclear region or the nucleus of the atom. The nucleus consists of or is composed of the proton and the neutrons. Okay, the protons and the neutrons are together locked inside the nucleus right over here. The protons and the neutrons, whatever number of protons it has, whatever number of neutrons it has, the nucleus is like a cage and it has locked the protons and neutrons inside it. No new neutrons, no new protons can enter, or the previous ones, the older ones, can exit from here. Okay, so they're locked inside. So this is a no-go region. The third subatomic particle, the electrons, we used to say that they do not exist inside the nucleus. They exist around the nucleus, right, in the extra nuclear part. So the electrons are basically revolving around the nucleus, and they are not present inside the nucleus. In fact, they are moving particles, and they move around the nucleus in circular orbits or circular shells. Okay, so these electrons are present in the extranuclear part, or the third body part of the atom is present in the shell of the atom. Now let's move on to a few points that you used to write. The first point was that regarding to the protons and the neutrons, that the protons and neutrons are closed inside the nucleus, protons and neutrons are closed inside the nucleus. The electrons are outside the nucleus. Outside the nucleus. These are all the things that you have learned in O-levels about the atomic structure. Outside the nucleus, revolving around it, or the nucleus, revolving around the nucleus in shells. We also call them orbits. We also call them energy levels. The next point would be, since the neutrons and the protons are closed inside the nucleus, they can never be gained, never be lost or shared with anybody. Okay? So the next point is that the protons and neutrons are locked inside the nucleus, inside the nucleus. So they can never be shared, lost or gained. Right? And what about the electrons? The electrons are not locked inside the nucleus, they're shells, present in shells. So they can be lost, gained, and even shared. So electrons are allowed to be lost, gained, or shared, but the protons and neutrons they cannot be lost, gained, or shared. Okay, they're locked inside the nucleus. Now let's move on to some of the properties of these subatomic particles. Okay, so let's make a table of subatomic particles. So we have the subatomic particle. We have three subatomic particles. There is proton, there is a neutron, and there is electrons. Right? And proton, what's the symbol for proton? It's a small p, or like a lowercase p with a positive charge. So that means protons are positively charged. What's the symbol for a neutron? It's a lowercase n with a zero charge on top of it. And electrons, E with a negative charge on top of it. Now let's talk about the charges first. Relative charge. What is the charge of a proton? Every single proton has the charge of 1 plus, right? 1 positive charge. Every proton carries a charge of 1 positive. The same way, every electron should carry a charge of 1 negative, right? And what about neutrons? Zero. Yeah, they're not charged, so they're neutral, so zero charge, right? And let's talk about their masses also. And we'll then generate a new point about the structure of the atom and the mass of the atom. What about protons? Protons, we know that protons have a very significant mass of 1. We'll use the unit later. Okay, so 1, the mass of a proton is 1. The mass of an electron is negligible, but the mass of a neutron is also 1. Okay, now we can't use kgs, grams, even grams or micrograms is a very large unit to be used at atomic scale, right? So what we need to do is we needed a new unit for the atomic scale, and we introduced a new unit that is known as atomic mass unit, or you could just write AMU. Now this is a very tiny or very small scale unit for the atomic level. So the proton basically has a mass of 1 AMU, which means 1 atomic mass unit. A neutron also has a mass of 1 AMU, that means 1 atomic mass unit. But an electron has negligible mass. The value for the mass of an electron, you could write it as 1 over 1836. That means if you divide 1 by 1836 or 1836 times, If you divide the value of 1 with 1836, the smallest value that you get after that, let me just solve it for you. 1 divided by 1836, that is about like 5.4 into 10 is power minus 4. Do you understand like scientific notation? Okay, so let me just convert it into ordinary weight. That is about 0 point double triple 0.005 AMU. So compared to the mass of a proton and a neutron, the electron's mass is comparatively insignificant, or we could call it negligible mass, right? So already we're at an atomic scale where the mass, the unit of mass is very, 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 very minute, right? And then you move on to 1 AMU, that is considerably significant, and then 1 AMU, and then you move on to like 0.00005. That is a very insignificant value. So what we say is electron has negligible mass. So basically it is non-existent. Mass-wise, we say that electrons have no mass. Okay, they do have mass, but that mass is negligible. Now let's consider an atom. Now we said that atoms have protons, neutrons and electrons. What two subatomic particles right here in the structure of the atom are basically contributing in forming up the mass of the atom? Who has that significant mass? Yes, exactly. So protons and neutrons have the significant mass, so they will contribute in building up the mass of the total atom, right? But the electrons having negligible mass, no matter how many electrons are present, their mass is still negligible compared to the protons and neutrons, right? So we say, we'll write another point, that first related to mass of an atom. According to the table, protons and neutrons contribute in building up the mass of the atom, but since electrons have negligible mass, negligible mass, they do not contribute in the mass. And what about the charge of the atom? Let's find out another point related to the charge from the table. Which two subatomic particles contribute in building up the charge of the atom, but one of them does not? Who is contributing to the charge? I'm not talking about the mass anymore, I'm talking about the charge. Yeah, protons have charge, electrons have charge, both of them will contribute charge wise, but the neutrons having no charge will not contribute charge wise, right? So it does not contribute any charge to the atom, only the protons and electrons do. But if we just write a single point about neutrons, what would that be? That neutrons are contributing in the mass and building up the mass of the atom, but they do not contribute in building up the charge of the atom, right? Similarly, protons are contributing in building up the charge and the building up the mass. But what about electrons? Electrons only contribute in building up the charge, and they do not contribute in building up the mass because they have negligible mass. Understood? Okay. So let's just write one more point, that protons and electrons E negative contribute in building the charge of an atom, but neutrons are neutral charge wise, so they do not. Okay, So right now we're still at O levels. We're just skimming through everything we learned in O levels, and now in about like two more two more topics we have to cover, and then we'll move on to A levels. Now let's move on to the atomic structure, and in that we have to move on to the shells and electronic configuration of O levels. Now in O levels we used to say that there is this ball-like structure in the middle of the atom. Then there is this first shell, and we used to call this first shell as our K shell. Okay, we call the first shell, the first orbit around the nucleus, as our K shell. The second shell is known as the L shell. So you just move alphabetically after that. L shell. Then there's this third shell around the nucleus, which is known as your M shell. And then there's this fourth shell around the nucleus, which is known as your N shell. So the K shell is your first shell, L shell is your second shell, M shell is your third shell, and the N shell is your fourth shell. Now in O levels, we used to say that this K shell, which is the first shell, can only accommodate how many electrons? Two maximum electrons, right? Two electrons can fit into the first shell. Then we had the L shell, which could accommodate about 8 electrons, and same goes for the other shells at O levels, right? So M shell would have, the third shell would have 8 electrons, and the N shell would also have 8 electrons. This was O levels, right? So as you move away from the nucleus and you just go to the the further shells, you'll just have to fit in 2 electrons in the first shell and then 8 electrons in the consecutive shells that come after that. Now we will fill electrons in the shells right here. So according to O levels, 2 electrons must be filled in this shell, no more than 2 in the K shell. Then in the L shell, you could have 8 electrons, so 1, 2, 3, 4, 5, 6, 7, 8. And in the L shell, after the L shell, the M shell, you would also have 8 electrons, 8 maximum electrons, no more than that in O levels or IGCSE. And then after that, we would also fill 8 electrons in the last or the fourth shell, which we call the N shell. So basically, you're just following alphabetical order to name the shells, right? This was the atomic structure that we studied in O levels. Clear up till now? Yeah, all good. Okay. Now, let's move on to something that we call an element and the symbol of elements. So basically, you have a periodic table in which all the elements are basically mentioned, and all those elements and their atoms containing the number of the protons present in their atoms. All elements are basically different identities of atoms, right? So basically, you broke down atoms into simpler forms, and then you found out that there are different types of identities of the atoms. And what were the identities of the atoms? They were based on the number of protons they have, and the number of neutrons they have, and the number of electrons that they have. So you found different types of atoms that had different types of neutrons, protons, and electrons, and then you had to name them, so you named them elements. Finally, you found out that, for example, there's this element called sodium, Na1123. Now first you have to figure out that what these two numbers mean and what this Na means. This is the symbol of the atom, symbol of the element basically. This is the symbol for the element. So basically this is the symbol of sodium. It is an element. Now you have two numbers. There is this smaller number and there is this larger number. The smaller number represents the atomic number, or in easy words we call it the proton number. This tells you that an atom of sodium would have how many protons in it? 11. Yeah, exactly, 11. And this larger number up here, this larger number, this tells you the nucleon number, or we also call it the mass number, and we also call it the relative atomic mass. We'll discuss this later when we reach moles. But right now, this is the nucleon number for you. You'll always call this the nucleon number. Okay, so let's figure out what the proton number tells you. So the proton number tells us the number of protons in the atom of an element. The number of protons in the atom of the element. Now, in order to understand the nucleon, you have to understand one thing first. What are nucleons? Nucleons is basically a name given to protons and neutrons collectively, right? If we put them together, like one subatomic particle is known as proton, the other is known as neutron, but collectively they're both known as nucleons. So protons and neutrons are collectively known as nucleons. Basically, the nucleon number, what does the nucleon number tell you? It tells you the sum of protons and neutrons in the atom of the element. So basically, it's the sum of protons and neutrons, the nucleon number. So basically, 23 is telling you that sodium has, that after you sum up the protons and neutrons in sodium, what number will you get? 23, right? So this larger number written on the element tells you the sum of protons and neutrons. For example, if you have another element, aluminium 1327, what does 13 tell you? That aluminium has 13 protons. But what does 27 tell you? That protons, yeah, protons and neutrons summed together are totally 23. Now, could you find out how many neutrons does it have? Yes, we could find out how many neutrons it has because we know the number of protons and we know that the protons and neutrons are collectively 27. So can I find neutrons from here if I subtract the number of protons from the nucleon number? I can, right? Yep. So the number of neutrons would be like 27 minus the proton number. That's why we used to subtract the small number from the bigger number, because the bigger number represents the sum of protons and neutrons. And if you subtract the number of protons from it, you'll be left with the number of neutrons. So if I subtract 13, I'm left with 14, which is basically the number of neutrons in the atom. Okay, and none of these numbers tell you how many electrons the atom might have. None of them. But we know for a fact that every atom in the universe is initially neutral charge wise. So if it has 13 protons, if your aluminium atom has 13 protons, that means it has a charge of 13 plus. Every single proton has 1 plus charge, so 13 protons would have 13 plus charge. Do we see any charge on the aluminium atom over here written as 13 plus? No, because it is neutral. So every atom in the universe is initially neutral. So that means if it has 13 plus charge, the 13 plus charge should be cancelled out with a 13 minus charge, right? So that means if it has 13 protons which were giving out this 13 positive charge, there should be 13 electrons in order to cancel out that 13 positive charge, right? So that means that every atom in the universe is initially neutral. That means then it has the same number of protons and electrons in order to be neutral, because both of these are charged particles. So if aluminium had 13 protons, that would mean since it is a neutral atom initially, it would also have 13 electrons, right? And what about sodium over here? If sodium had 11 protons, how many electrons would it have? Would a neutral atom of sodium have? 11. Yep, 11 electrons. And what about the neutrons? Neutrons you can find out from the nucleon number. So the sum of protons and neutrons is 23 in this case. Then proton number is 11. So 11 plus neutrons would be 23. If we subtract 11 from 23, or the number of protons from the number of nucleons, we can find out the number of neutrons, which is 12 in this case, right? Yeah. So now that we've figured out how to find the number of electrons in every atom, we can arrange these electrons in shells. Let's make the atomic structure, O-level atomic structure so the O-level atomic structure for example, sodium. So sodium had 1123. How many subatomic particles does sodium have? It has 11 protons. We figured out from the proton number. It also has how many neutrons? 23 minus 11. So 23 minus 11, that would be 12. It has 12 neutrons. It has 11 protons. And since it is a neutral atom, how many electrons should it have? 11 electrons. 11. Yep. So it has 11 electrons. Now we need to arrange these electrons in the shells. That is called your electronic configuration. Now what is electronic configuration? It is basically the arrangement of electrons in the shells of an atom. So it has 11 electrons. Sodium has 11 electrons. So sodium, these 11 electrons, we are going to arrange them in shells. So this is the nucleus. How many electrons does the first shell accommodate from these 11 electrons? Only 2. Yep. How many are you left with? You're left with 9 more. So you have to move on to the next shell. And the next shell, which is the second shell, it can accommodate how many of these 9 electrons? Only 8. So you have to move on to the next shell. How many are you left with? You have filled 10 electrons. You're left with only 1 more electron. So that last electron goes into the third shell, right here. So this last electron will be right here. So we just arranged the electrons in the shells. Now let's do this for example, calcium. Calcium is 2040. So how many protons? 20 protons. How many neutrons? 40 minus 20 would be 20 neutrons. And how many electrons? Since it is a neutral atom, it should have equal number of protons and electrons, so 20 electrons. Let's arrange these 20 electrons in the electronic structure. So this is the nucleus. This is the nucleus. This would be our first shell. I'll just shade the nucleus. This is the first shell. How many electrons? 2 electrons. Then this is the next shell. We need that for accommodating 8 more electrons. 1, 2, 3, 4, 5, 6, 7, 8. Now we're done with 10 electrons. 10 are still left, so we have to move on to the next shell. So moving on to the next shell, how many electrons according to O levels can this accommodate? 8 electrons. So now we're done with 18 electrons. We need to fill 2 more electrons. How will we fill 2 more electrons? We will move on to the next shell. according to O levels again. This would be the electronic configuration. Now you need to memorize two facts. From this electronic configuration, you can find out the group number of the element, and you can also find out the period number. Let me just explain what the period number means and what the group number means. So in the periodic table, the elements are arranged into vertical columns, as you can see, and horizontal rows too, right? So there's these vertical columns right here, like this, and there are about 18 vertical columns, and there are these horizontal rows right here, right? So these vertical columns, like this one, these are known as your groups. These are known as your groups, and the horizontal rows, these horizontal rows starting from here, from hydrogen's horizontal row, we call them periods. Okay, so let's just count how many groups we have. We have a total of 18 groups if we count these 10 groups of transition elements that are in between group 2 and group 3 right here. If we do not count these, if we forget about these, then you have group 1, the first vertical column, group 2, the second vertical column, then you just move on to group 3, 4, 5, 6, 7 and 8. So that would make 8 groups if we do not count 10 groups of the elements that are in between right here. These are called transition elements. Okay? But if we do count these 10 groups, then group 3 would be group 13, group 4 would be group 14, group 5 would be group 15, and then so on. Till group 8, you'll have group 18. Then how many horizontal rows, that means periods you have? You have the first period right here. Then you have the second horizontal row right here. This is the second period. This would be the third period. This would be the fourth, fifth, sixth, and seventh period. Okay, these are 7 total periods. Now, these are not separate elements that we have mentioned right here. These were supposed to fit right over here in this section. These elements belong in this section, but because of the length of the periodic table would be very long if we accommodate these inside the periodic table that we have made above them, above the table we have made the right here, over here. So that's why we just took them out and we mentioned them separately. And we do not have to work with these. We only have to work with the first 7 periods and some transition elements and some groups. So basically, how do we find our group number and period number from the electronic configuration? And this applies to A levels electronic configuration as well. Okay, now you need to memorize two things. The group number is equal to the number of valence electrons. So you just make the structure of the atom or write down the electronic configuration. This is the first application of electronic configuration. How will you find the group number? You will find the group number by counting the number of valence electrons. What are valence electrons? Yep, outermost electrons. So how many outermost electrons does calcium have? Two. So what would be the group number of calcium? Group 2. And what about sodium? How many outer electrons does it have? So group 1. Now let's just confirm this from the periodic table. Is this true? So this is group 1, right? The first horizontal, first vertical column. Can you see sodium right here? Yes. Yeah. And what about calcium? We said calcium is in group 2. Is it in group 2? It is. So this applies for all the elements except for hydrogen. Okay, hydrogen is not part of any group. That's why it's separate from the whole periodic table. And also does not apply on helium because helium has 2 outermost electrons, but it is the part of group 8. So these two are exceptions. Rest of the atoms or elements, these rules apply on. Now let's move on to the period number. How do you find the period number? You find the period number by the number of shells in the atom. So how many shells does calcium have? There's 1, 2, 3 and 4. So what would be the period of calcium? Yeah, it's in period 4. That means it's in the fourth horizontal row in the periodic table. Same goes for sodium. How many shells does sodium have? 3, so it is in the period 3 of the periodic table. Right? So now let's use these two facts to locate an unknown element that we do not know the identity of, but we do know the electronic configuration of. So let's find element X, 15 and 31. Now let's locate X in the periodic table by just the electronic configuration. So do you remember the straight line electronic configuration we used to write in O levels? We used to write like the electrons in K shell, then a comma, the electrons in L shell, then a comma, the electrons in the third shell, then a comma, and then the electrons in the fourth shell, then a comma. This is known as the straight line electronic configuration. So it has a total of 15 protons. So it should have 15 electrons because it is a neutral atom, right? So what about these 15 electrons? How would you arrange them in shells? How many electrons in the first shell? 2. Then you move on to the next shell. How many electrons in the second shell? 8. And how many electrons in the next shell?
8.
You're only left with 5.
Oh yes. 15.
Yeah, right? So 15 electrons will be filled like this. Now let's just apply the rules. We need to find which group X belongs to, so the group number, and we need to find which period X belongs to. Then we'll locate it in the periodic table. What's the group number for X? Which is the valence shell? Is this the valence shell or the last?
Yeah.
Yep, the rightmost is the valence shell. How many electrons in the valence shell? 5. So group number should be
5.
5. You always write the group number in Roman. Okay. And what about the period number? How many shells are filled over here? 1, 2 and 3. 3 shells are being used, so period number 3. Now let's locate this in the periodic table. We have a group 5 and period 3 element. So go to the periodic table. Let's first find out group 5. Let me clear the page. Okay. Where is group 5? This is group 1, 2. Ignore all of these. 3, 4 and 5. So we are at group 5. Let's make a vertical line over here. And we're at period 3. So where is period 3? This is the first period. Then you move on to the second period. This would be the third period. So are we at period 3? Yep.
Yeah.
So let's draw a line from here too. Where are these two lines intersecting?
Phosphorus.
Where? So which is this element? Phosphorus. So it's phosphorus who belongs to group number 5 and has 3 shells or period 3. Okay. So that's how you can use the electronic configuration in order to locate your elements. Okay, so that was all about O levels that you needed to know. Now let's move on to the A levels update. The first update in A levels is that you have the same atomic structure. You do not need to change the atomic structure, and we will use the IG electronic structure that we have made in order to find trends for different atoms or different elements in the same group and in the same period. Okay, so let's move on to A levels update. Now you need to, the first update for A levels is a note. You need to memorize this note, that the total number of electrons in any shell are no longer 2, 8, 8, 8, 8, 8. You will find them out using shells as 2n square. You will use this formula now. This is the first update, where n is the number of the shell. If it's the first shell, you put n as 1. If it's the second shell, you put n as 2. If it's the third shell, you put n as fourth, and then so on. Right? So let's just now make another electronic structure or atomic structure and find out how many electrons this first shell should have. So this shell is the K shell, the first shell. How many electrons should the first shell have? Now you don't use the memorized value, you calculate it. So according to 2n square, since it is the first shell, what would be the value of n? 1. So what would be the answer? 2 electrons. So same goes for O levels. 2 electrons in the first shell, so 2 electrons right here. I'll just unpair them instead of pairing them. Let's move on to the next shell. This is our second shell. It's known as the L shell. Just follow alphabetical order. You do not need to memorize this. Just memorize the first shell is the K shell. Then after that it's just alphabetical order. So this is our second shell. Let's find out how many electrons the second shell should have. So 2n square. N should be put as 2 because this is second shell. How many electrons would this be? 8 electrons. Right? So 2n square becomes 8. That means this will have 8 electrons. 1, 2, 3, 4, 5, 6, 7, and 8. Let's move on to the next shell. This is our third shell. This is known as the M shell. And the M shell is the third shell. So 2n would be 3 and squared. What would be the value of it? 18. 3 squared is 9. 9 times 2 is 18. Now this is where everything changes. In O levels, the third shell used to have 8 electrons, but now it has 18 electrons. So we will fill 18 electrons right here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. So now it has 18 electrons. Okay. And let's move on to the last shell. How many electrons should the last shell have? This is our last shell. Yep. So this is your N shell or the fourth shell. You can write first, second, third, fourth if you tend to forget these. N shell should have 2, N should be 4 and square. What would be the value? 32. That means this shell can accommodate not 8 electrons but 32 electrons. So let's just fill 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So these are the number of electrons this shell can accommodate. Right? This is the first update. So now we have a new formula to calculate the number of electrons present in every shell. First update. So what's the second update? Second update is a fact now. Every single shell consists of subshells. So you have the first shell, it will have a subshell. You have the second shell, it has subshells. And then there's the third shell, it also has subshells. And then there's the fourth shell. The fourth shell will also have subshells. Okay, so every single shell has subshells. Now you need to memorize the subshells. Let's memorize the names of the subshells. Now we name subshells like S, P, D, and F. These are the four subshells that can be present inside shells. Okay, or you can call them The shells you can call energy levels, and these are the sub energy levels inside the shell. Okay.
Yeah.
So up till now, we have moved inside the shell. We've like magnified inside the shell, and we saw that there weren't any electrons over there. Instead, you found subshells inside the shells. Okay, so we have moved from shell, we magnified, we found subshells. The shells we had K shell, L shell, M shell, and N shell. In the subshells we found there's an S subshell, P subshell, D subshell, and F subshell. Okay, so let me just draw one of the shells right here. For example, this was the nucleus, and this is the first shell, and I'm going to highlight the first shell. Inside the first shell, this blue line is your subshell. The highlighted part is your shell. So you magnified, you found a subshell inside the shell, right?
Yep.
Now, if we further magnify, we'll find another thing over here, but we'll move on to that later. First, we need to establish a connection between shells and subshells. So what is that connection over here? So we'll just write shell or the shell number. Then we move on to the number of electrons, and then we move on to just move on to shell and then subshell. First, you need to establish a connection between these two. So when you're at the first shell, you have only one subshell in the first shell, and that is an S subshell. Always start with S. For any shell, always start with S. Okay. Now we will link why there is only S subshell in this subshell or in this shell, but for now just memorize. In the second shell, when you move on to the second energy level, you have two sub energy levels, which are S and P. And in the third shell, when you move on to the third shell, you have three sub energy levels, S, P, and then what should be the next one? This should be D. And then when you move on to the fourth subshell, you find there are four energy subshells, which are S, P, D, and F. So how do you name these subshells? It's the first shell's subshell, so you write 1s. These two subshells, S and P, are from the second shell, so you write 2s and 2p. The rest, SPD from the third shell, are from the third shell, so you write 3s, 3p, and 3d. And then there's the fourth shell to 4s, 4p, 4d, and 4f. Okay, this is how you name them. Because you can see the S subshell in the first, second, third, fourth shell of the atom, right? So in order to distinguish between them, we have to give them names. So we name them according to their shell number. Fine?
Yes.
Okay.
Yeah.
Now the next thing, you just have to memorize for now because you will get used to this. You have to remember that S can accommodate a total of 2 electrons, no more than 2. The S subshell, I'm not talking about the shell, I'm talking about the subshell. Similarly, the P subshell can accommodate a total of 6 electrons, so 0 to 6 it can accommodate. The D subshell accommodates 10 and the F subshell accommodates 14 electrons. So quickly memorize this. S can accommodate 2 electrons, P can accommodate maximum of 6 electrons, D can accommodate a maximum of 10 electrons, and F can accommodate a maximum of 14 electrons. So 2, 6, 10, and 14. Done? So let's move on to number of electrons. Why do they have so many subshells? When you move on to the next shells, why do they have more subshells than the first shell? Because the number of electrons that the first shell has to accommodate are how many? Use the formula 2n square, 2 electrons. And can S subshell alone accommodate these 2 electrons? Yes.
Yes.
Now what about the second shell? Apply the formula 2n square. How many electrons does it totally have?
It has 8.
8 electrons. Out of these 8, how many go to S and how many go to P? Now since the S subshell has a maximum capacity of 2, the remaining 6 electrons will have to go to the next subshell, which is P, and it can accommodate 6 electrons. So how many in total? These two subshells were needed to accommodate 8 electrons totally, right? What about the third shell? The third shell accommodates a total of 18 electrons. So it needs 3 subshells. Why? Because out of these 18, 2 go over here. Then you have to move on to the next subshell. How many go over here? 6. You're done with 8 electrons. You're still left with 10. And can the D subshell accommodate the last 10 electrons? It can. So how many in total over here? 18 now. So easily accommodate, right? And what about the fourth shell?
18 for the third one.
Yep, 18 electrons for the third one. And why does it have 3 subshells? Because it needs 3 subshells to accommodate a total of 18 electrons. If it had only S subshell, it could only accommodate 2 electrons. What about the remaining 16? So it needs to have a P subshell which can accommodate a further 6 electrons. Now you're done with 8. 10 are still remaining. So it has to have a D subshell in order to fulfill the remaining 10 electrons. Okay. And the fourth subshell 2n square, how many electrons? 32 electrons. These 32 electrons in the fourth shell will be filled inside subshells, right? Every shell has a subshell. So these 32 electrons, out of these 32 electrons, how many would go to 4s? 2. How many would go to 4p? 6. How many would go to 4d? 10. How many are you done with right now? 18. You still have how many electrons remaining?
17. 14.
14 electrons are still remaining. And does the F subshell allow you to accommodate 14 remaining electrons?
Yes.
It does.
It does.
That's why the fourth shell needs a 4F subshell also.
Yeah.
Okay. So now you understand the relationship between shells and subshells, right?
Yes.
So you have to practice this a little bit so you can get like you have better flow in it. You'll be fluent in this then.
Okay.
Okay. Now let's move on to the last thing for today. So right now we're at shells. We magnified the shells and we found out about subshells. So we had shells, we had 4 kinds of shells, K, L, M and N. Then we moved on to subshells. We had S, P, D and F subshells. Now we'll magnify further. If you magnify further, you'll find that inside these subshells, you still won't find electrons, you'll find orbitals. Found out orbitals. Now, there are no separate names for orbitals. You don't have to name the orbitals. But let's zoom in. When we went inside this subshell over here, we found out that there is this orbital right here. This is our orbital now. What's an orbital? You have to know the definition of an orbital. So basically, around a nucleus, let's just define it right here. What's an orbital? So in O levels, we used to say that orbitals are basically circular paths around the nucleus and the electrons are revolving around the nucleus. That is wrong. Okay? Electrons do not revolve around the nucleus. They have very random movement. So if this was a nucleus, electron would have a probability of, you'd have a probability of finding the electron anywhere in this region, right here. So random movement, at every instant of time, you'll find the electron in a different place or at a different dot that I'm drawing over here. And then you'll also find it somewhere over here, right? So this is the probability of finding electron in like around the nucleus. So electron, don't imagine this as an orbital right here and the electron be revolving around here. No, it is not. It's not revolving. It has random movement, but in a specific region, right? So this region around the nucleus, this region around the nucleus, where the probability of finding electron is the greatest or maximum, you call that space the orbital. You understand what I'm saying?
Yes.
This region around the nucleus. Now you would find the electron on these spots too. But where is the maximum probability of finding the electron? In this region, right? So the region where the probability of finding the electrons is maximum. The region where finding the electron or the probability of electron is maximum. That is known as an orbital. Okay? Or you could also say is 95%. So the 95% of the time electron will be around this region over here, but at 5% of the time you will also find it outside this region, in these spots. So what is an orbital? It is basically the region around the nucleus where you will find the electron 95% of the times. Okay? And you have to memorize a fact about orbitals, that one orbital can only accommodate how many electrons? 2 electrons. A single orbital can only accommodate 2 electrons. Clear?
Yeah.
Okay. Now what we'll do is we'll link shells, subshells, orbitals, and the number of electrons. So the first shell, now this is the last thing. After this we will wrap up the class, but we have to do this before ending, okay? So we can connect this in the next lecture. So the first shell, so are you okay with it if I take a bit more time?
Yeah, that's good. That's okay.
Let's just connect these. The first shell, how many, okay, the first shell had, this is the first shell, we call it the K shell. How many subshells does the first shell have? Or don't say that, just leave it. How many electrons should the first shell have? Let's link it with electrons. 2 electrons, 2n square, right? You apply the formula 2n square to find the electron. 2 electrons, okay. For these 2 electrons, how many subshells does it need?
Only one.
Only yes, 1s, right? Now the 1s could accommodate how many electrons?
Two.
2. So the first subshell is enough to accommodate these 2 electrons. Now in order to accommodate these 2 electrons, this s subshell must have how many orbitals? Because one orbital can only accommodate 2 electrons. How many orbitals does the s subshell have? Only one. So there is only one orbital inside the s subshell. To accommodate both these electrons, I'm going to show these electrons as arrows. Okay, one arrow represents one electron and two arrows represent two electrons.
Okay.
For now, they're just arrows. You don't need to even discuss why they're single-headed or why they're opposite in direction. Just forget about it. So one orbital was needed. Now let's move on to the second shell. About the second shell, let's link the electrons first. In the second shell, how many electrons? 8 electrons. So in order to accommodate 8 electrons, how many subshells? You'll have the 2s subshell, which will accommodate 2 electrons out of these, and then you'll have the 2p subshell, which will need to accommodate the remaining 6 electrons. Right? So these are the subshells. We'll just link the subshells. Now link the orbitals with it. If s is accommodating a total of 2 electrons, how many orbitals should it have?
It's 8, so it's 4.
S subshell. I'm talking about just S. Forget about the P subshell right now.
Oh,
Yeah.
so it's 1.
Yeah. S subshell has one orbital to accommodate the first 2 electrons, and the P subshell should have
3.
3 orbitals in order to accommodate the 6 electrons, because one orbital can only accommodate 2 electrons. Right? Let's move on to the next shell. The third shell has how many subshells? 3.
3.
It needs to fill in 18 electrons, and in order to fill in 18 electrons, it will need an S which fills up 2 electrons, it will need a P which fills up 6 electrons, and it will also need a D subshell in order to fill the remaining 10 electrons. Right? So 3s, 3p, and 3d. Let's figure out the number of orbitals inside each subshell in the third shell. So S would have one orbital. P would have to have how many orbitals?
3.
3, because it has to fill 6 electrons in this subshell. And D would have how many?
5.
Yep, 5 subshells, because it needs to fill 10 electrons, and just divide 10 by 2, 2 per orbital, so you need 5 orbitals. Okay, and the fourth subshell, fourth shell, that can accommodate 32 electrons. How many subshells does it need? It needs an S to accommodate 2, it needs a P to accommodate 6. Now there are a total of 8 electrons. Moving on to 4d, now you're at 18, and the remaining 14 would be in 4f subshell. Now how many orbitals does S have? 1. How many does P have? 3. How many does D have? 5. And then how many does F have? 7 orbitals. Clear?
Yeah.
Okay. So this is how we're going to find out how many shells and orbitals each subshell has, or how many subshells each shell has, and then how many orbitals each subshell must have, and then how many electrons each orbital has. Okay, this is how you link. You start from shells and subshells, then you move on to orbitals, then you figure out how many orbitals you need for each subshell in order to fill the total number of electrons that were going to be filled in the complete shell. Okay,
Yes. Yeah.
so now let's go back to our diagram. And so this was our first shell, the highlighted part. We zoomed in, we found out that there's this blue thing over there, which is known as the subshell. And then inside that blue thing, you found an orbital. And inside that orbital, you finally found what? Yeah. What did you find? Yeah, exactly. Inside that orbital, you found electrons. Let me just draw it with some other color. You found electrons over here. Okay. Now in the next class, we're going to basically arrange all of these, and then we're going to look at the diagram, and then we move on to the electronic configuration and its applications. Okay. So that's all for today. I'll just send these notes to you, revise them very thoroughly, and initially you do have to memorize this, but once you get the gist of it, you'll just be in, like, you'll have to just practice it to get the flow of it. Okay.
Yeah.